Okay, so we're recording and we're live. All right, so people should start jumping in.
I think there was an issue with the time change, though. I saw Jennifer Cooper saying that it was 3 o'clock for her, so I don't know if we might end up with less people than normal because of...
She's here. Hey, Jennifer. Yeah, it doesn't matter for her. Hey, guys, how are you? While you're joining, please tell us where you're hearing us from, please. Okay, people are... Okay, they're joining. Hello, everybody. If you're hearing us well,
Hi,
please
Jennifer.
say yes and where you're hearing us from, please. Hey, Dallas. Abhik, I think I'm saying that correctly. Abhik from Phoenix. All right, Abhik. Okay. Alana.
Ada, I think. Is that?
What? What are you saying?
Is that
Guadalajara.
Ada from Atlanta?
No. Oh, yeah, that's true.
Oh, hi, Jose.
Hey, Mexico City.
Hi, Alfredo.
Yeah. For some people, I mean, if you know someone who wants to join and they're not sure on the time, this is the time. So please tell them.
I think we're going to be a little late today.
Yeah. So please tell them and tell your mom that we're live so she can hear us too. All right. So I think we're going to get started. Hello, everyone. Very happy to be here with you. And right now we have an amazing guest. His name is Sean Martin. You can see him right there. And we also have John Reuter. And they're from the company called Cambridge Semantics. And the plan for today's talk is a little interesting title we have, that is data ingestion and manipulation in the data fabric. And so first, thank you, Sean and John, for being here with us. Sean is the CTO of the company, and John is the VP of marketing. So we're happy to hear from you.
Thank you very much for having us. I hope you can hear us clearly.
Yeah, we can hear clearly.
Yep.
Thank you, Fabio. Thank you, Kristen.
Thank you.
Yeah, thank you.
All right, so I think we can get started by the people who don't know who Sean or John is. We can start hearing from you where you're from, what you're doing, just your background.
Sure. So Sean Martin, and I, as Fabio just said, I'm the CTO here at Cambridge Semantics and one of the founders. Cambridge Semantics is approaching its 12th year, I believe, so it's been a long haul here. I grew up in South Africa and came to the US about 20 years ago via the UK. This is really my second career. My first career was as an IBMer, which is how I ended up getting moved so much. IBM stands for I've been moved, if you don't know that.
I like that.
So I started IBM, as I said, as an intern, spent 15 years with them. The last 12 of which were quite interesting, is they kind of the reason I think I ended up in Cambridge Semantics. I was working in and started a skunkworks in IBM that was working on the original internet technologies in the mid-90s. So I was lucky enough to be in a position to see a few things coming down the road, and I built the first application server for IBM, which we used before IBM had any products or anything like that around internet. We were showing off the internet to IBM and to IBM's customers at things like Wimbledon and the Atlanta Olympics and the PGA Tour golf. So I put most of the big sporting events online.
Yeah, that's nuts.
95, 96, and we built a lot of interesting technology, sort of web application technology at the time, geographical scaling technology. So that was the beginning of my career, and that was popular enough at IBM that I got left alone for the next probably 10 or 11 years to do my own things. I had a foray into JavaScript runtimes for desktops and phones, which I finished around 2000. So things that anticipated Chromium, sort of the Chrome desktop, and what Microsoft did with their HTML rendering in the desktop. And then, of course, Apple and Adobe Air. So all of that work we did quite a few years ago, just probably a year or a few years ahead of its time, unfortunately. But it was the springboard that got me into semantic technologies, which was so interesting that a number of us, 9 of us, left IBM and started Cambridge Semantics. And why we were so interested in semantic technologies is because we were looking for technology that would allow us to do late binding of data from different places and apply it in a late fashion to services that were all very well described in a way that was less. At the time, all we had was really the state of the art was XML schema. And they're not a good way of tying things together late, because you need to write a program to do it. And somebody who was working for me at the time went off to do his PhD down the road at MIT. And he was in the AI lab, funny enough, which is right next to C-Cell, which is where the W3C is. And he came back and said, hey, I found this thing. It's called RDF, and it's a triple, and you build graphs out of it, and you can provide models that explain what elements of that graph mean. And this is an interesting technology to solve this problem of how to bring data together late. And really the original problem was how to evolve applications much faster, because we were working with biomedical researchers who were coming up with new concepts, and they were trying to model and do in silico modeling of various kind of cancers. And we ended up building a system to store all these models, and we were looking for something way more flexible than what existed. So that was kind of the original use case that we built on, and did that for 4 or 5 years at IBM. We actually did 3 versions of the system, so middleware that supported these graph standards, and then IBM had a lot of reorgs, and the air cover executives who had kind of sponsored me through my career all retired. And suddenly our team was exposed, but rather than get reabsorbed to do something else in IBM, we thought this area was so promising, we left and started Cambridge Semantics. And now we're about 100 and something people, mainly out of Boston, although we have an office in San Diego. Something happened along the way, which probably is kind of seminal, which is we joined forces with a gentleman called Barry Zane, who has a history of building massively parallel data warehouse technology. He was the brains behind the Netezza, one of the brains, I guess, because it was a tough product, but one of the brains behind Netezza, which is a very successful appliance for doing data warehousing. He then built Parexel, which these days that code base is better known as Redshift in Amazon. And then he and others spun out of Parexel to create a company called Sparkle City, which was going to be the same sort of thing as Parexel and Redshift, except in memory and graph. And when Cambridge Semantics people found out about that, over a year or two became obvious that we should all work together. And his team joined us. We acquired the assets that they had built so far. And that product now is on the market as Anzo Graph. And it's the raw graph technology under the rest of our product, which is called Anzo. Anzo is now in the fourth generation. So we did 3 generations at IBM. It was open source. And then we left IBM, forked it, did a 4th, really the first Cambridge Semantics. We called it Anzo at that point, and now we've done 4 since. So I guess we're in the seventh generation in total of the technology, 4th at Cambridge Semantics. And the Anzo technology sits on top of the Anzo Graph technology. Anzo Graph gives us this massive scale capability, and Anzo provides all the tooling and middleware and visualization and ETL that we need to actually bring data in and get it and manage it in Anzo Graph. So that hopefully gives you a little bit of context for me. It's a lot of story, but there is a progression if you look at it backwards. John?
Thank you. I'm the VP of Marketing here at Cambridge Semantics. I've been here now for about 4.5 years. My role here is more as a silent observer, but since you see my name and I've been introduced, I'll just tell you that my career has spanned the data spectrum all the way from time sharing to PCs to supercomputer to internet to where we are now with graph. My fascination has always been around how people work with data, how you access it, how you manage it, how you analyze it, and ultimately, what is it that you want to do with it? So effectively, it is people, process, and technology. And one of the things that drew me to Cambridge Semantics was in my career, I've been in the areas of enterprise search, database marketing, business intelligence, et cetera. And I really saw graph and semantics as the closest thing that people have come to date in terms of being able to readily access their data and make more insightful decisions from a rich set of data. So thank you, and I'll turn it back for the time with Sean.
Thank you, John.
Thank you.
All right, so I think that's an amazing history. I think while I was trying to understand how to create a Hotmail account, you were creating the internet in some way. So,
my brother Simon, who is part of this company, and he's our product architect, he and I both wish that we had done Hotmail, because it would have been much quicker than and WhatsApp and Instagram. I mean, there's a number of things we've seen over the years that we wished, well, that would have been much easier, well, probably much easier to have done than what we've actually done, which has proved to be very, very difficult indeed.
So I think right now one of people may be wondering, so you mentioned semantic technologies. What's that supposed to mean?
Well, semantics, there's another joke about semantics, which is that it's supposed to be the study of meaning, but it's one of the most ambiguous terms out there. So sort of a grim irony of the term. But for us, it for the most part means adopting a set of standards that provide a way to share in a machine and human readable way models of meaning across the world. And we're using W3 standards W3C standards that Tim Berners-Lee and Jim Hendler and Aurel Assian and a couple of other people put together that allow you to capture the meaning of data from a human point of view as well as a machine point of view in a form that is somewhat universal. And that ontology language we use is OWL. In Cambridge Semantics, we use it to capture business meaning. The models of business or whatever the organization is that we're working for. They have a way of thinking about their data, talking about their data, actually their business, I should say, rather than their data. They have ways of thinking and talking about their business. And the data is always a reflection of that thing. But generally with traditional technology, it never matches up. The data always is never as true to that, is never a true model of the actual underlying business. It's always an approximation, and generally a pretty low fidelity approximation. And one of the first things that disappeared was the names of things. So we are trying to use semantic technology, this set of standards, to put business meaningful terminology back into and reassociate it with the data, so that the models, the underlying models that you want to do your analytics on and reflect are much more true to the reality of the domain, the business or the research area that you're in, and so on. So that's what semantics means to us. As I said, it means a number of other things to other people, often a lot less specific than that. But generally, it's about adding business meaning in the context of IT.
So it's like the opposite of a data lake.
It is the opposite of a data lake, or at least the first generation of data lakes. We knew that data lakes were going to be good for us. Our previous sort of iteration of the Anzo product was to help manage data lakes, but we've set our sights a little higher now. Now we want to manage all of the data.
Yeah, and I think you mentioned that. I mean, if you go to the webpage, you see you're building something closer to the smart data lake. So
that was the last sort of generation of the product, where we were really, what we anticipated was a data swamp. As soon as people start just dumping data willy-nilly from applications without documentation, or it didn't, it was almost immediately after people started using Hadoop and HDFS that's true. it was pretty obvious it was going to become a total disaster. Since then, there's been a whole category of application that has come out called a data catalog, where people are attempting to put some sort of order around this. But the data sets you see in data lakes tend to be either dumps of sort of binary dumps of files, like documents and images and so on, or they tend to be tables. And the coherence across them is not there. And that's actually where we get into the stuff that I'm really interested in, which is how a data fabric can help you blend data from many sources, including many tables. So the world has tended, where for structured data at least, tended to be tabular and relational. And the problem with those representations is they really do force a much less accurate view of the underlying reality, because ironically, relational databases are not good for holding connections between different pieces of data. It's a force fit, even though you have keys and so on. There are things that get in the way of modeling data, and in particular, the fact that you have to upfront model your schema just to hold data is a real huge practical. It's like carrying two cannonballs around with you everywhere you go, because you just have to do so much more to manage them, just to get data into the right form. Your queries are very complicated to write, and then if you change anything,
it becomes a mess.
It becomes a mess quickly, and adding new data is terrible because it breaks so much stuff. Because you've got this very carefully curated. In a big enterprise data warehouse, it may have taken you a year to figure out what all the table, what your various physical and logical data models are, and all the tables you need, and all the connections between them. And there's obviously and how you're going to name things, and your enterprise data dictionary potentially. All that stuff you've taken a long time to do. And then the business keeps saying, I need this data, I need that data, and they keep buying data, or the internet has exploded the sort of availability of data, and getting all that corralled in is, we worked with a bank some years ago. I remember they had a 6-month cycle. If you wanted an extra column in a table report, it was a 6-month cycle to get it, and it was $10,000 per column.
But what's that pricing? It's like I don't get it.
It's a big, very large bank that everybody knows the name of. But my point is that it was so heavy and so weighed down, and that was the way that you actually aggregated data for sort of cross data set reporting and enterprise data warehouse. So the data lake was a sort of, I think, a reaction, a revolt against that. And the business users said, well, just give me the data and I will deal with it. And I'm sure we've people on this podcast who know the webinar that know how to handle data themselves, and they can, but that is not a very evenly distributed skill. Most people cannot.
And it would become your whole job too. You couldn't,
absolutely.
trying to
probably more than your whole job. Usually.
Yeah.
It's usually
be a lifer just making sense of a data lake.
Well, I've read the statistic. I have no way of validating, but they say that something like, for data scientists, more than 70-80% of their time is spent corralling data. So they can maybe get at it, but then they're missing the context, the meaning of it. They have got to keep going back to people who maybe created the data, or people who know the applications where it came from, to understand what does this column really mean, or what does this code in this column reference. All of that is just hidden away because we've tried to corral the world into tables, and we had good reason for doing that in the 70s and 80s, where we didn't have the massive compute capacity to be able to compute our way out of that. You were doing things to be as efficient as possible, and so you had to keep kind of dumbing down your models and so on, and worrying about where your indices were, and being very careful how you wrote your queries and all. And I guess for ledgers and the kind of applications people were building then, that was good. But now it's really just a huge bottleneck, and worse, it can't handle unstructured data. If you're doing text analytics on whatever your emails or your documents or presentations or lab reports or patients' complaints or whatever it is, and you're pulling sense out of those, how do you get all those facts into a table? It's very difficult when really there's an explosion of types of things you find in a text document. So you can either have a table, per type of thing you find, and if you find something that doesn't have a table associated with it, you have nowhere to put it, or you drop it on the floor. So the extraction of data into tabular forms tends to be a very lossy extraction, whereas with graph, you just keep growing it, which is wonderful.
But so in the process of your explanation was amazing. You mentioned the concept of the data fabric, right? So I think before jumping into ingestion, automation, or managing data on the data fabric, I think we should be understanding. I mean, now we know what semantics, and we're using graph and knowledge graphs. So what's the point here of the data fabric?
So at Cambridge Semantics, we had a fork in the road where we had to decide what the best use case for graph technology was. And we have sort of two classes of things. One was building applications that could be evolved very rapidly, and using ontologies to drive the structures within applications. And the other one, I think, and the one we chose, is the killer application for graph, which is data integration, and on top of that, technologies like machine learning and so on. And so we chose that, and really the vision for the company from very early on was to establish what we now call the data fabric. So everything we've done over the last 12 years, we've never pivoted as a company. We've really just been building to this single vision nonstop, and it's taken a very long time because we've had to build every part of this technology stack, all the middleware, all the databases, all the visualization, all the ETL, all the tools. And finally, now having built all that, we get to build the data fabric. The data fabric is this overlay that sits on top of all of the chaos of your information landscape in an enterprise. You already have many data management tools. You have many silos of data. You have warehouses, which have become silos. You have data lakes. You have catalogs that try to help you locate and find data sets. You have a massive amount of shadow data that's been generated at the sort of individual and department level that is not managed by IT. You have vast stores of unstructured data that no one really has tried to do anything with, perhaps apart from search in the last, say, 10 years.
Yeah.
John was at Fast, was one of the companies that was trying to do something with search, but it was really just find documents. It wasn't extract really deep meaning from documents, and more than that, tie that meaning to the meaning in other documents or in other sources. So the fabric is really designed as the beginning of the cure for that. It's an overlay technology. So it's not like SAP, where back in the 80s or 80s and 90s when you wanted to adopt SAP, you had to throw out all your existing systems, and it was very expensive and very painful to go on to SAP. It's not like that. And because the technology, the standards are designed to be a sort of an incremental that are like the web. They grow and get more valuable the more you do, but you can start with just something very, very small.
But that will be one of my first questions. Like, okay, so I think most of the companies out there doing machine learning and big data, they're using stuff like Hadoop, they're using Spark, they have Oracle, and they're using their Python notebooks or something like that. So, I mean, what would be the change? I mean, and I think if you're hearing us here as a podcast or in webinar live, I think one of the issues you have when you're turning on your computer and try to get into a job is to understand the data you have. And you have to ask someone else, hey, where's this data located? And how can I access this from HDFS? And then they need to give you permissions, and you need to install something else. And then you have to go, and then you have to understand the tools for understanding your data. So, and what if, I mean, I think one of the things that are happening right now is people are migrating their data from Oracle to their data lakes, or from MySQL or Postgre to their data lakes. So now that this is happening, and this is the reality right now, that we have all these data lakes or swamps, whatever you want to call them, how can people jump into this new technology? I mean, if I have all these things and I bought all these different tools, how can I jump into this new wave?
Well, so, I mean, those tools are not going to go away anytime soon. Yeah, it's true, we are seeing plenty of our customers, and we sometimes help them migrating off, last generation data warehouse technology onto data lakes and other kinds of approaches. But there's billions of dollars of infrastructure that's been tested, and I don't know if you know the statistic, again, unverifiable, but I believe it. 50% of data warehouse projects fail. So, there's a massive cost of actually setting up a data warehouse and getting it working. There's a good chance.
I believe that because I have been through a project to set up a data warehouse, and it was painful. And like all the data governance and the data stewards and getting everyone together in a room to decide what this metric that was maybe defined 6 different ways across 6 different departments. Now you need to collaborate and determine a single meaning to that. Holy moly.
So there's a lot to go wrong there. So if you've got it working, there's strong disincentive not to mess with it. And that's the way of, why this will be slowly absorbed. But the question we come back to is, how does one begin to establish a data fabric? And what is a data fabric? A data fabric is that layer over the top of all this morass that you can gently build out an application, or we call them data products, a data product at a time. Each data product producing something of value to some targeted business problem. Maybe it's an extraction to do, some kind of machine learning or something like that. But it's something that has value, and you do it a little bit at a time. And what you're doing as you do that is you're starting to map the data from the chaos into the fabric. And the fabric is a coherent layer with semantics and a lot of metadata that you start to coalesce to make that data increasingly identified, understood, and future-proofed. You're using a set of standards and including with the data, the meaning of the data. The key thing about I mentioned ontologies, the models earlier, that is a graph as well and can be part of the graph, so that where data can travel with the meaning of the data, you start to future-proof that data and make it much more reusable. You don't need to, you've got some agreement as to what things mean, and you're now maintaining that along with the data. And so you are essentially starting to build a network of all your data, and there's a network effect that will apply. The more data sets you join into this network, the more valuable it becomes. And all of that data remains there for uses in the way the standards work is, if you map data into those standards, the integration is simply selecting a data set and another data set, and they immediately can be blended together. Unlike XML, where you need a program to tie 2 data sets together, you literally need it to go through and figure out, to parse the XML. With the underlying graph standard, we use RDF, you can just commingle the data from 2 graphs, from 2 discrete data sets, and that is effectively a blend. You then may want to create additional graph elements that connect up those graphs that you've combined, but you can immediately put them together. So using these standards makes all of that data reusable in an incremental way. It's an overlay technology. It sits on top of anything you have. It could sit on top of data coming out of a mainframe, out of data that's coming out of a very modern IoT stream. It wouldn't matter where the source or sources of data is. They all end up in this graph, growing the graph. And the graph is really a logical graph that, for practical purposes, we can use our in-memory technology to take portions of that you select and put them in memory to do clever analytics on and prepare them for modeling and so on.
Okay, so just to clarify, so the data warehouse isn't going away.
It's data
so this is so a company has, maybe they have Salesforce data that they never integrated into their data warehouse. They've got a data warehouse. They've got a big data environment, and this is a layer over the top. And blending is when you're saying that all of your siloed sources are now going to become part of, the data is going to be all available from a single source, in a sense.
Well, connected up, yes. And
connected up.
Yeah, and the key here is if you think about how it's relatively difficult to do a join, right? If you've arranged a database or a data warehouse, you've arranged data with keys and so on so that you can write a query that will join different elements of data together.
Well, and then you create if you have a star schema, then you create a cube,
Exactly. So but think about how many entities you can actually realistically or practically
way more than what's in there. I get you.
Exactly. Right. So imagine if you didn't have to do that. Imagine if you could just describe where the join is as a connection between 2 points, two nodes in a model. And that's what the graph technology is offering. And really that model offers you a map of all the possible ways that this data from all these different places connects up. So the model, if you like, it provides the business meaning. It can do more than that, of course. You can code things into the model around inference. In fact, you can annotate the model to add arbitrary additional metadata that might be useful. But the key for me, the key value of it is it's a pattern of all possible joins. And one of the coolest things about the graph database technologies in general is and particularly our one, because it's highly parallel in memory, is you don't have to know up front how you're going to query it. You've got a map of all the possible joins, in other words, the connections between anything. You can start at some place in the graph, and you've got it in your heads. Imagine, a node with a line that is a relationship that connects it to another node. This node may be a person. The connector maybe has prescription. The next node is a drug. Maybe there's a connection to the doctor that prescribed the drug, and there's a connection from the drug to the place where it was made, which maybe ties you back to a trillion things around clinical trials and 12 years worth of data that was needed to bring that thing to market. It's an endless chain of how things connect. That you can make your map as rich and as wide and as broad as you need to cover all the things you care about and how they connect together. And if a new thing comes along, you simply need to say, well, logically, how does this thing connect in my head as a human? How do I connect this particular kind of data or representing this entity to the rest of everything else? And if there isn't a way to connect it, it probably is telling you that you need some other data in between that you need to go and get. And the model describes all of that for you. It's as you build it out, you see where the holes are in your understanding of the business that you're trying to represent, because the model is really a model representing some domain of information that you as a user understand.
So the way you'd write to retrieve that data, how complex is that? And are you talking in terms of like, you have this starting point, and are you talking about how many levels away you're going from, like?
Yeah, you can be, yes. So this is where we start to get into the query languages and the algorithms.
Yeah, that's what I want to hear about.
So the query language Cambridge Semantics uses is another standard. So it's in fact, we use a family of standards, but there are other query languages out there. The one we use is called Sparkle, and it's a W3C standard. And it's really a superset of SQL. There are other popular languages out there. Neo4j has a language called Cypher. OpenCypher is the beginnings of an attempt to make that a standard. And I know there's work, we're interested in it ourselves, and we're interested in Cypher, actually. There's also Tinkerpop and Gremlin, which is another way that people write programs against the graph. So there are various sort of de facto and actual standards in existence. They all do more or less the same things. People will talk about property graphs versus RDF graphs. All of that's kind of gone away now because all the people who implemented RDF graphs have added properties. So there may be a non-standard way of getting properties, but you're comparing against a bunch of non-standard query languages anyway. So it kind of comes to the same thing. But the short of it is you start somewhere in the graph and you are describing connections through the graph as you traverse different sort of entity types, nodes, and instances of those entity types. So you go from, I don't know, patient to drug to doctor, or from patient, maybe there's two connections, patient to doctor and patient to drug and drug to doctor, and then doctor to drug company. those are the connections that are codified in the graph, and your queries simply can either ask for those connections and say, how is this patient connected to something somewhere else in the graph? And the system can figure out, with an algorithm, for example, shortest path, what the connections are and how many hops there are. That is very different from a relational database where you'd have to ask explicitly, is the patient connected like this, or is the patient connected like that? And you would have had to have arranged your data in the indices to actually get that answer. So one of the very nice things about these graph query languages is they are far less constrained about how they ask for queries. Another really important thing is that because we're taking the hit up front for trying to connect everything up, and there's no indexes in the case of our system, the other thing that's very nice is that we are arranging all the data in a conceptual model, right? It's a hard work to get a conceptual model if you're using relational technology. You end up with a physical and a logical model, but you struggle with the conceptual model. Often that's added more as an application or reports to make it understandable. But the models we use are really already at the conceptual model, the human consumer description of the data. And that makes writing the queries much easier, because you're now able to use the model as a map. Each arc in the model is really a relationship that can have a human readable name. And we have query builders that allow you to start a drug, and you can see, what's connected to drug. Look, there's a doctor and a patient connected to drug. I'm going to traverse the patient link, and now I'm at a patient object. And what are the properties on patient? Oh, look, there's a property that talks about they're employed by somebody. Oh, look, they're employed by a company, another link. So you can essentially trace, using the model, the connections, and underneath the covers, we can generate automatically, in a way that is very difficult to do with SQL, we can generate the queries that will bring back what we want to find. So you've got...
Yeah, so that's one of my questions. So while you're mentioning data discovery and all these different things, so in the platform you've created, you don't have to write those queries, right?
Correct. And that's a very good thing, because nobody wants to learn another query language.
Yeah, but so, let's imagine I'm starting in a new company and they have ANSO, an ANSO graph. So, and they tell me, hey, take a look of this. So how can I go there and understand my data with ANSO and ANSO graph? Well,
there's you and there's most people. I think we'd be lying if we said that there's a certain conceptual ability that people need to understand all their data, sort of, who can think about the data in a more abstract way in terms of the model. So I think there's always going to be people who are more adept at preparing data and creating the models and figuring out how things should be connected up. And those are really your data scientists, your data engineers, your data analysts. How somebody who's less adept will use the tool is more through an extract or through a custom-built application. So I think that's where state-of-the-art is right now, and hopefully there'll be an awful lot of automation that increases the number of people who can be directly exposed to the more complicated parts of data engineering as time goes by. But realistically, what we're trying to do is enable the people who are adept at that data engineering to be way more productive. We're talking an order of magnitude at least more productive once all the tooling's in place. So if you, Fabio, were going to a place, you would be right in there looking at the models, traversing. You'd probably actually learn the query language pretty immediately as well, and you would take to it like a duck to water, because it is really just somebody has figured out how to many somebodies have figured out how to kind of compress a lot of the stuff that you find painful and repetitive and just boring but has to be done. They've started to find ways to compress all that and to remember it so that you don't have to do it twice for the same data and so
So I have another question.
Yeah.
So before you were talking about how difficult it was to get a new column added to a table going through the standard processes in your company for a relational database. So now let's say you've got your data fabric all set up and then you buy some new software and get a new, new columns of data, new feed that you want to add. Like, how difficult is that to integrate into
That's the
your
wonderful
graph?
thing. That is much, much easier. What you do is you look at that data, this new data that's coming in, or maybe it's an extra. Well, at this point, we're mostly using this as a sort of a reporting fabric. So you tend to be lifting data up and reading it. Although I said there is a whole transactional story, but that's going to take a lot more time and software to deal with. But let's go back to we're mostly doing reporting and trying to aggregate data for machine learning or for analytics reporting, that kind of thing. To bring in a new data source is as simple as look at that data and understand how conceptually it maps into the data that you've so far brought into your fabric. Don't forget the fabric will keep growing as you add data sources. And you initially will create a model or find a model that exists already and do a mapping onto that data. One of the things I'm hoping that the machine learning technologies will increasingly help us do as we aggregate more and more of these in a way that is collected, we'll be able to use machine learning to automate that mapping. I think that one of the advantages of a big picture approach like this is you will end up with enough examples that are curated that you can actually imagine us really doing this very well.
Yeah.
There's a company called Tamer that is starting to do this quite well, I believe, in the clinical trial space, for example, where they're actually having some success in bringing in new clinical trials and aligning them over the top of existing clinical trial data, which is something businesses want to do. The fabric should really accelerate the ability to do that. But anyway, you're mapping the data onto some sort of conceptual model. Conceptual models out in the wild are starting to become, ones in OWL, in the standard we're using, are starting to become, OWL is becoming the way that you end up describing some domain of information. So in the financial services business, there's a model called FIBO, which describes everything, every relationship, every entity type in the financial services business. It's absolutely enormous. There's another one that's emerged called CDISC, which describes clinical trial data, and so on. That's going to become take a model like that and map to it.
Can we talk about that for a second? Because you've mentioned medical data a couple times, and they're obviously notoriously, like health insurance companies, they're some of the most siloed, difficult data to work with. Are they open to?
So that's a very interesting question. So I think that healthcare is very complicated because there's so many cores, so many applications, so many elements. But we are certainly starting to hear about customers in healthcare and actually insurance as well as another industry, and even in the credit industry, where they are looking to partner or I don't know if you called it, what are they kind of frenemy with their competitors, where they will use. We have a technology called data layers in the graph where we actually can keep logical collections of data separate in terms of access control, but then bring them together for the purposes of aggregation and modeling and querying in a very granular fashion, so that only those who are allowed to see what they're allowed to see. You could imagine using either a system like ours that has these multi-graphs or data layers that are segregated as a way of aggregating data and starting to see benchmarks, or insurance companies are interested in this because it may help. Somebody who commits fraud is likely not just to only have fraud against Geico. They're likely to spread it around a bit. And so there's interest in sharing data, not in a way that they can use the data competitively, but use the data in a cooperative way. But we're now starting to talk about more and more advanced use cases of the fabric. I never quite finished explaining how easy it was to get another thing in. It's simply just add that model, and that model will have some factoid that connects it to everything else. Make sure you got that factoid in place. That's how you.
And those feeds that are real time, the graph will update.
It can. Now we're getting into your technology choices, right?
Yeah.
There'll be right now the graph graphs are relatively new. The first crop of graph technologies like Stardog or like Neo, very popular one, tend to be transactional oriented. So they're better for building applications on OLTP. Whereas AnzoGraph is really one of the first warehouse style graphs. It's like comparing Aurora or Cassandra to Redshift. They're really horses for courses. One is for very fast transactions. The other one is for looking for great big aggregates and complex queries. So AnzoGraph is the first really big, massively parallel OLAP graph. What I'm really getting at here is we're starting to now see enough interest in graph that we're teasing apart what happened in relational. And in relational, you've got people who specialized in real-time relational. And so too, we will see technologies, some company out there will think about doing a really well-optimized real-time streaming graph. Or we might decide that to add that, spend some time and money and add that in a way that is very efficient in AnzoGraph. I mean, I think we could do streaming already, but maybe there's things we could do better. So you'll find that as time goes by, there's more and more specialists, but that has nothing to do with the data itself. It's just a characteristic of the data. We still need to connect the data up. We still need to give it meaning, and we'll use the same methods for doing that, regardless of how fast the data is coming at us. And the metadata that is part of that data can tell you things like, how long to keep it. So if I've got a stream of events, I may not need that to persist in my database for more than a few minutes or a few hours. It just depends on what the underlying application is. Or I may need to keep it forever, in which case I'm not only looking at it live, and I'm also probably writing it to some kind of archival files.
Not in memory.
Yeah, but
that's orthogonal to the kinds of data.
So one of the things that are always bugging me is that, you mentioned you've been doing this for 12 years. And
well, it's more like 20 now in semantics, if you count the few years at IBM, but yeah.
Yeah, actually, so, and I think we're hearing of the power of the technology. Mm-hmm. I'm a data scientist, or I think I am a data scientist. What's the? We're learning all this difficult stuff to deal with data, and they're not easy at all. And it takes us months and years to understand them, and that shouldn't be that hard. I think if we take, there are surveys, and people are the most annoying part of data science is trying to understand, clean, and prepare your data. So,
but here's news though. That has always been the problem with data. Even before, the data science has got very interesting recently, simply because of these very fast.
Yeah, that's the history of using data.
BI and reporting has had the same nightmare for many decades. So I would say welcome to the club on that one.
Yeah, but that would mean why isn't it more famous? What's stopping us to really understand that maybe using graph technologies and semantics are easier than doing the other?
It's a very good question. So the real reason, I think, comes down to the same reason the machine learning is now viable. It's massive parallel compute, relatively cheap, lots of RAM, fast networking, and being able to apply that in our software stacks. We could, when I started with this semantics at IBM, so say 2001-ish, 100,000 facts using Jenna, which was a popular stack at the time. It was out of HP Labs. This was a research stack for RDF now. 100,000 triples was a lot. We were mapping down onto relational databases, which is an ugly map, and with a graph to relational is very ugly. It's slow. And it was just a non-starter. And everybody went around saying, why are you messing around with that? Graph will never scale, right? But there was always this underlying arc of technology that, Moore's law or whatever's come next is changing that equation. And I made the bet a very long time ago that we would start to solve these problems, because what I couldn't see was another path to doing data integration that didn't really require what is essentially introducing an additional level of abstraction. As we map things into this conceptual model, we're really abstracting it to add the metadata of meaning to make this data easier to understand and deal with. The reason that you never had it before is they just didn't have the horsepower to compute it. Barry Zane says that, if we'd had graphs that could have performed like the one we have now, relational would never have happened. So I would say that it's taken us this long to rewrite all the software to be graph aware and graph friendly, top to bottom, understand the models, the conceptual models, top to bottom, and put all that in. That's a lot of software to have written. Yeah. You couldn't really use much of anybody else's software because it just didn't fit with what we were trying to do. So not only did we have to write all that software, but we needed that really, really screaming and cheap compute to tie it all together. So we're at a moment, just like machine learning, where the stars are aligning to actually make this possible. And what I'm very excited about, and I think you are too, is that we're actually going to make these two worlds collide too. And that's coming. That's what the next year or two is about.
Awesome.
Yeah. So one of the things that people can I mean, we have some questions, by the way, and we're gonna get them very soon. One of my last questions will be, so I'm a data scientist and I'm working with SQL and Python and Spark in my notebook. And there are some data engineers that are helping me getting my data clean or prepared for that. So where does Anso and Instagram fit in there? I mean, where's the actual thing that I'll be seeing changing very fast when I join these semantic technologies and when I see all of this changing in my company?
So I think the roadmap is something like the following. So we're busy down in the foundational work of trying to solve those problems about cleaning data, reusability of data, identifying data, and making it reusable as the first step. And I think we're pretty close now with that. Close enough that we can now credibly start to build out these semantic data fabrics for lots of data sources. As a byproduct of what we've done, we've managed to build some pretty interesting technologies around very high-scale graph transformation, low-level capability, and more means for automatically generating a lot of that transformation, using the models to guide what the join patterns are and to help you insert functions and so on. You now have all your data arranged for you in a graph. And I think we could start to, and this is concretely what we're doing, we're adding to the end, this is a warehouse engine. It has the normal kind of windowed aggregates and all the roll-up functions and all the things you'd find in Redshift, right? You go read the Redshift manual. We have all of that. But what we've also have been adding, obviously, are the graph algorithms that allow you to get additional sort of information signal using, I don't know, PageRank, shortest path. And there's a bunch of those, and they're just, there's various correlations and things. Assume that you'll see all those, and you can go to any graph vendor, and they're all got a list of those things. So we're adding all of those too. But also, in addition to that, what we've done is we've talked to some data scientists, and we said, what are the most important algorithms you need that are sort of the next phase down? If I did a normal extract of a CSV and said, okay, that's the, it's a very wide CSV, it's got a lot of features in it, and I'm going to throw it over to you to put into pandas or whatever your favorite ML environment is, what are you going to do next? And what you're likely to do next is run a whole battery of analytics against statistical or analytics to understand what it is you want to do, how you want to transform it. All of those algorithms, or a large number of them, we're pulling up into the graph. So that, because what you want to be able to do is play against the graph, and the table that you're going to pull out always to go downstream, at least for the moment, is really a denormalization query against the graph. You're trying to create a flattening of the graph structures, and you're selecting against all sorts of things that maybe are on the edges of the graph to build you a table, and the properties are coming from all over the graph. So you're building out that table. And that table is your feature set. Now, what can we do to help you identify which column should be in that table, A. B, what can we do to help you identify the transforms to apply? Should I bucket this? Should I pivot it over and spread it out into 15 columns? You guys are far more familiar with what you're going to want to do there. There's no doubt that the output into a machine learning system is very different to what I would use for reporting. The actual final we may all want clean data and integrated data and identified data. Actually, you care less about it being identified as long as it's clean, because you can throw machinery at it. But it helps when you're integrating it to identify it. But the question now is, what can we do to make more and more be done before it takes time to do that extract. It takes time. For each column that you have to create is probably a subquery somewhere against data in the graph. And you don't know what parts of the graph are going to provide, or in combination, are going to provide the best signal. So how do we speed up the process and hopefully automate? For example, we can run something against the graph where we understand every join pattern. We bring back every property with its type. We can understand where the instances, where it's populated and where it isn't. That immediately reduces the space of where we might want to get our feature variables from. And we can start to automate. I think we're going to get to sort of a deep feature synthesis approach this way, through automated query and through introspection of the types of the data, and a battery of algorithms that you would normally apply a little bit further downstream, but we can now apply them directly in the graph. That's probably the very next phase, because it's kind of obvious. I think after that, and what we're doing to help this is allowing the algorithms that are the machine learning algorithms to run in parallel on the graph directly in the same heap space as the data. Now, in our system, it's an MPP, so the entire data set is spread across however many nodes you need to hold it. And when we create a query, we actually take that Sparkle query, that SQL or Sparkle, whatever it is, incoming query, we convert it to C++, and we compile it, and we distribute it across the cluster, and we run it. And for every thread, in every machine across the cluster runs that a part of that query. So we're going to have to figure out how to break that down. And what we're doing is starting to expose that through initially Java. I would like to see Python as the next one, so that you can then start to put in parallel algorithms for every thread that's working in the cluster can pass a bit of data out. And this is for actually doing the training, but also later on for very quickly growing the graph through inferring or predicting data in real time, being able to push those models right out into the edges, I don't know if it's the edge of the cluster, but across the cluster, so that every cluster member who's got 32 threads or 64 threads, however many there are, is in parallel doing the prediction for that part of the graph. So that's what I see over actually quite close in. We're getting pretty close with our Java API. So part of this, of course, is to make the whole thing more accessible. See, currently our APIs are all C++. How do we get that to a wider audience? I think we've got Java is a pretty obvious one, because it enables my own development team, who's very Java skilled. It lets us get at more data sources and so on through JDBC. But the very next one would be to look at communities that are interested in doing interesting things on top of Graph. I think Python has to be very high on that list. So we could then bring in all those Python libraries. But people are going to have to think about how to run those algorithms in parallel. Because if you're not, you're going to end up bottlenecking. It'll work, but you'll end up bottlenecking on leader nodes that are kind of, where the query, part of the query becomes a prediction, if you like. So there's a subquery ends in a prediction that then the rest of the query carries on. If that can only run in one place, then you're going to have a very slow query that bottlenecks in one place in the overall cluster. But that sort of, for me, I'm just finger painting here, is the roadmap that we're on.
Awesome.
In this company, at least.
Thank you for that, Sean. I think the place you're getting is clear, and there's a lot of job. I mean, I just hearing you talk about it, we know there's a lot of things to do. So we're really glad someone's doing it. So we're gonna wait and see.
What I'm hoping is that once we actually get these APIs out there, a community of interest can spring up around picking it up and doing the thing. We're not, this company doesn't specialize in machine learning algorithms. We're really data engineers, data warehouse people, middleware people, ETL, visualization people. And the plan for making this real is really to enable a wider community of people who really do get the next phase and can see and tell us what is needed to get to that point. So I'm hoping that these APIs and we'll have there's going to be an Anzo graph, which is the raw engine. There's going to be a community, a free community version that will run on people's laptops. I mean, it runs on a laptop under Docker. Actually, it runs on my laptop. I'm running Windows under WSL. So, there's a version of this that will run locally on people's machines. We've already enabled Zeppelin as a notebook to interact with it directly. So if you want to learn Sparkle and directly interact with the graph, you're going to be able to do that with this free version. Anzo graph is a much bigger system. It establishes the whole fabric. One of the things I'm interested in doing is a mini fabric, more of a personal edition. But there's a lot of packaging that needs to be done to get to that point. So there's things that hopefully will be out there very soon that people in the data science community can immediately just try out and see if they get benefit.
Awesome. So I think we have time for answering like one or two questions. So the first question will be from Jennifer saying, so just I'm clear, data fabric is equal to data lake?
No. So data fabric is really, the data lake is a place you're aggregating data. The data fabric is where you provide meaning and you blend data. So it's a layer above the data lake. The data lake has turned into, it seems, for the most part, just a great big place to drop data, hopefully with some metadata that describes it. But it tends to be thousands of discrete files and tables, maybe described in the catalog. You'd see it through Hive or something like that. Whereas the fabric is really about knitting together data from across all of that and other places. And it's another layer in the stack. I think data fabric is more of an architecture. Cambridge Semantics provides kind of a pinnacle of that architecture, that's sort of the blending and semantic layer of it. That's our part in an overall data architecture, but everybody plays a part. The Hadoop guys in Cloudera and Horton, they're part of the journey of data. And so the data overall architecture includes a massive ecosystem of existing vendors and technologies. And then we're simply something that provides this missing piece on top, this knowledge graph that can tie the meaning of the data and the data elements together in a way that will make sense. Hopefully that helped.
Yeah. So I think that answer Jennifer's questions also on is if you're using the data lake term to mean the enterprise knowledge graph. So the answer will be no there too.
Yeah, that's correct.
All right. So I think Jennifer has a question for how to get trained or how to get training on the data lake technologies. So I think there's a lot of ways to do that. Sadly, we don't have much time to continue with that, but you can please write us, and you remember that there's a lot of great free and paid tools for learning, like Udemy and Coursera and all of these different things. So I think we need to wrap up, and we thank you very much, Sean and John, for being here with us. It has been an amazing experience, and I think our audience has been really interested of what you have to say. Can we please hear where people can hear from you, where they can take a look of your website, your blog information?
Sure. We have a website, which is www.cambridgesemantics.com. And there's a blog on that website. People are free to email me. I'm just Sean, SEAN, at cambridgesemantics.com. And that's the main way. I think, John, you handle our outreach. We're a lot of trade shows over the year.
Two things I'd suggest. One is you can go to cambridgesemantics.com, and there's a lot of content that you can download to further learn about all this. Additionally, we have something called Semantic University that I would point people to. That is they're full of tutorials and all kinds of educational materials for people who are trying to better understand semantic and graph.
Awesome.
I forgot about that one. Yeah.
Thank you so much, Sean. I feel like I learned a lot, and I really came to this conversation really confused about what's going on. And I'm not saying like I know what's going on, but like I was starting to get what you were putting down.
Well, I'm hoping we can get to a coherence. One of the biggest problems actually with semantics and graph technology has been explaining it and finding the right sort of metaphors and examples. So that has been another barrier, apart from just the technology being unready and not scalable for a long time. Just explaining what we're doing has been a real challenge. So I'm not surprised that you can.
All right. So as a reminder, this video will be on YouTube later. And we're also launching our podcast very, very soon. So you'll be able to hear that on Spotify, iTunes, Google Play, wherever you want. So whenever you're hearing this, if you're hearing this 10 years from now and you're using semantics for everything, we're sorry. We're just starting. So
Time capsule.
this is time capsule. So thank you very much, Sean, John, and Christian for being here.
Thank you so much for having us. I hope it's been useful for everyone.
Great.
Bye. Thank you.
Thank you so much. Bye.